So, doing the 3.6 homework by myself last night.
Yeah. Makes sense?
So, cool. It's not easy. I mean,
Not easy.
one thing I noticed is your foundational mastery of algebra shines through on your calculus grades.
Wow. Are you good?
There were, I mean, I was sad with how many points I had to take off for people not distributing negatives on the test or not understanding how to write an equation of a line, because that's from algebra, and it's right here, point slope form, rules of exponents. There were multiple times rules of exponents. We don't know how to use rules of exponents. Like the big example, this is like things people missed and things that have nothing to do with what you're doing in my class. So if I have x squared and I put it to the third power, literally, when in doubt, write it out. When in doubt, write it out. Oh my God, guess what? This is actually, this is going to be x to the 6th.
Isn't it just added?
No, you multiply. So if you are multiplying the bases together, you add the exponents. If you have an exponent to an exponent, you multiply. So this is the quotient rule. There was one problem where it was like you have to square the bottom. That was something people missed. Like not distributing negatives, just not doing like computation correct. Like that was some problems that people missed, and it was nothing to do with the chapter. A little worrying. Okay, so 3.7. If you guys have questions over the test, look over what I wrote. I literally wrote so many things. While I'm talking, go ahead, put your phones into the holders, like it says on here, phones in red holder. This is not new. This is quarter 2. You need to have your phones in the red holder. If I see your phone, regardless if you're on it, you will get points off. Just do it. That was risky move. Risky. Okay. You have to get up anyway. Wow.
Yeah.
Wow. Wow, that was so nice of you.
Yeah, it was really nice.
Okay, so implicit differentiation. If you were at open house, this is what was in the speech of Anne Mizrahi, was implicit differentiation. And it's great. It actually is really great. She talked about it.
I wasn't there.
So, implicit differentiation. So, if something is implicit, what does that mean? What does it mean to be implicit? Like, if something is implied, if something's implied, what does it mean?
It means they said it without saying it.
Saying it without saying it, because literally it's implied because I don't have to say it. We already know because it's inside our brains. Implicit is already, it's kind of like it's inside already. So implicit differentiation, we're trying to take a derivative, but guess what? Y is actually part of it. Crazy. So the issue is when, like, how do we find slope when we can't conveniently solve the equation to find the function, right? Because this is not a function. What I'm showing you is a circle. So how do I actually find the derivative if it's not a function? Because if I get y by itself, it's literally going to be the square root of plus or minus x squared, or 9 minus x squared. You said I did that, I subtracted and then square root. So y is plus or minus the square root of 9 minus x squared. Okay, well, this isn't going to be a function. It's literally a circle. When we have curves and circles, how do we actually find the derivative, right? So this is a big issue. So the answer is to treat y as a differentiable function of x and differentiate both sides with respect to x using differentiation rules for sums, products, quotient, and the chain rule. So now we're applying everything we learned in this whole chapter. We solve for dy dx in terms of x and together contain a formula that calculates the slope at any point. So that's what the book says. Thought that was interesting. Maybe not. Whatever. So I have this x squared plus y squared circle drawn for you. Up till now, we looked at things in terms of y. Y equals something. We didn't actually have like a y inside as part of our function. Oh my God, why is this not? It's not selecting. Okay. So pretty much up until now, we looked at things like y equals 2x squared plus 5x. This would be very easy for you to take a derivative of, right? So being differentiable means you're able to take a derivative. So I'm going to differentiate this. When you differentiate, you take a derivative. So I take dy dx of both sides. So I take d dx of both sides. What's wrong? I just hear this like whispering. Just pay attention, okay? Put your book back on the ground. Just pay attention. So when I take a derivative of both sides, literally the left side turns into dy dx, and the right side turns into 4x plus 5. This is what we've done so far. Okay, well, what about this circle that we have? Take a derivative, so power rule. I'm sorry. Bring it in front. 2 times 2 is 4. X to the first power.
No, I'm saying you just like. Are you just doing this y equals 2x squared plus 5x?
Yes, because this is what we've been doing so far. So it should be like familiar. What's not familiar is when I have a circle. So up here I have a slope of 0, but then I have a different slope here. Here is vertical. So I have all these. I'm trying to take all these tangents where I'm trying to draw a tangent line to the curve, aka it only touches at one point. The tangent literally shows you the slope at any point. So all of these lines I just drew, I'm trying to take I want the derivative, I want the slope at any point for my circle. So notice that this graph has a well-defined slope at nearly every point. So if I took a straight edge, this is heavy. Let's do this instead. Aha, here we go. So here's my straight edge. Here's a tangent. There, I can literally trace this around at every point and it will have a nice tangent. It's not super hard, you just have to have it meet at one point, right? So you see how it's just meeting at one point, right there? That's what I mean when I say the graph is a well-defined slope at every point. You can easily take a tangent line at every point. The process by which we find dy dx is called implicit differentiation. You treat y as if it's a differentiable function of x, and then differentiate both sides of the equation with respect to x. Okay, so what this looks like. We are looking at the top, x squared plus y squared equals 9. All right, I'm going to bring it down. Okay. So treat y as a differentiable function of x and differentiate both sides of the equation with respect to x. So I'm going to take x squared. Oh my god, why is this not writing? I think I need a new tip to this pen. This sucks. X squared plus y squared equals 9. Okay, now I'm going to do d dx of every single thing. So the derivative of x squared is going to be 2x, and then, how do I explain this to you? So I'm treating it as a function of x, so this is going to be dx over dx. And this one, derivative of y squared, I can say is 2y. Then you say dy dx, and you already know dx over dx is just 1. Did I skip? I think I may have skipped a step. Okay. I literally thought about this for 30 minutes yesterday, how I was going to show you this. Okay, so I'm going to take the derivative with respect to x. I'm going to take the derivative of this whole function with respect to x. I'm going to do it to both sides. You already know the derivative of a constant is 0. So this right side is equal to 0. Okay. So if I'm taking with respect to x, this first one, well, that's just going to be 2x. The issue comes when I'm trying to take the derivative with respect to x of y squared. Well, that's not an x. So we haven't done that before, right? If I had x to the third, you could easily take derivative, but this is y. So I'm literally just going to treat it as if it's a function. So I'll take the derivative, and then you would multiply it by dy dx. Don't know if this will work. Because you literally have to distribute out the dy dx, literally taking a derivative. So since we're going to treat y as if it's a function, like secretly somewhere else we have y equals some function. So that's what dy dx is meaning, is like, oh, it's actually going to be the derivative of y with respect to x. Because we don't know what this y is actually. No, that's not making sense. Thought I could do a better job in the book. Okay, so maybe like y is equal to some function, but instead of saying the whole function, we just put in y. That's what it means when it says treat it as if it's a differentiable function, aka take the derivative, act like y was an x, take the derivative, and then just multiply by dy dx. That's what I'm trying to show you over here, is when oh my god, show it. Come on. Okay, so that's what I'm trying to show you right here, is when I distribute the dx, the d dx, to the first one, that's just going to be dx over dx, so that turns into a 1. 1 times 2x is 2x. And then I have derivative of 2y multiplied by the dy dx. Imagine if I had a third variable, it would, like z, it would be dz dx. So literally you're just going to multiply by dy dx. Solve for dy dx in terms of x and y together to obtain a formula that calculates the slope at any point of the graph. Okay, what I have is 2x plus 2y times dy dx, and that's equal to 0. What? This is the same problem. It's like showing you step by step what to do. First, treat y as if it's a differentiable function of x. Then get dy by itself. So now I'm trying to solve for dy, like literally just get it by itself. So I'll subtract 2x on both sides. 2y times dy dx is equal to negative 2x. And now if I divide by 2y on both sides, you get the derivative. dy dx is just going to be negative x over y. So the issue stems from the fact that our function, at first, it's a circle. It's not a real function because it doesn't pass the vertical line test. So I can't just have a nice, easy function of y equals something. Y is actually like depending more. So y impacts the slope because you have multiple places where you are the y. This is really hard to describe to you guys. Okay. So literally, what you have to do, take derivative of x like normal, take the derivative of y, but then you're not actually done. You just say, okay, tack on the dy dx. That's really all you would have to know. Like you don't have to understand why this is a thing. AP Calculus doesn't even have to know why this is a thing. This is like a multiple choice level question. This isn't even the free response. Yeah. So when your friends in AP Calc are complaining, you should tell them that. You have one per year, as stated on your syllabi. Okay. That's the way it used to be, and now all the math teachers are in. Now we all moved it to one a year. It was one a semester, and then we had a math meeting, and we changed it to one a year.
But
and I would.
Off if you.
So the first time you're taking extensions 10. The second time,
10%?
20. Third time, 30. If you already use your extension, you come to me the day of. Huh? And it's like it adds 10 every time. That way people will take the test on time.
Every day it's later.
Every time you ask, it's an extra 10. So the first time you ask, it'll be 10 off. The second time you come to me the day of and you're like, I need an extension. Okay, cool. Add another 10, 20 off. No, like, okay, think about it. Why are rules in place? Oh, because of something. Why do I have this rule? Because people take advantage of it and come to me and want to take an extension every time for that 10 off. I'm not about that life. I don't want to encourage that, so I get an extra 10 every time. Yeah. And the extension should be like, oh my God. Like,
only one per year though.
because people were like, oh yeah, I got one left this semester. Heck yeah, I'll use it for this one. Like, no, that's not the spirit of it. The spirit of your extension is like, literally, this is crazy. It's like the one thing, huh?
They don't carry over.
They never did.
Who was the teacher who said that?
They never did.
Oh, I didn't
They're like, oh, I didn't use it. I might as well use it for the last one of the semester.
I'm gonna do it.
That's what happened, huh?
School Wednesday, Thursday, Friday, Thanksgiving, right?
We have school Wednesday, ends at noon.
Yeah, but we technically could still do that.
What? Yeah, but you only have one a year.
Yeah, but like,
So you could wait until the very last test. Yeah? But then it's one less time that people do that.
Next week we don't have.
All right.
Next week we don't have.
No, that's not all what we said. Thanksgiving is not next week. We have a full week next week. Let's keep going. Ready? Let's go.
First full weeks in September.
Yes. Find dy dx if y squared equals x. Okay, y squared equals x. So what I would like to do, hopefully this is a little bit easier example. Y squared equals x. Let's take the derivative with respect to x on both sides. So I have two, hold on, let me write this as y squared equals d dx of x. So what is the derivative of x with respect to x?
0. Nope.
1.
1. Oh,
It's just instead of saying 1 times dx over dx, it's like, okay, cool. Because you always have d of whatever variable you're seeing over the bottom, which is dx. Well, here I'm taking the derivative of x, so my variable is x, and that's why I can ignore it on the right side. But the left side, what? Because I'm taking the derivative with respect to x. It will be, so it'll be 2y times dy dx. And then to get dy dx by itself, divide both sides by 2y. So dy dx, I'm going to explain it. Hold on, I'm going to explain it in a moment, okay? Is equal to 1 over 2y. So, literally, implicit differentiation is when you don't really have a function. It's because you have more than one y value for an x. So if you have parabolas on its side, if you have circles, if you have like these spiral things, that's when you're going to be using it. So for example, find the slope of the point of 4, 2 and 4, -2. What is y squared equals x look like? Well, if it was x equals y squared, it'd be a parabola, but it's y squared equals x, so it's a sideways parabola. Yeah. So hold on. Let's see, 1, 1, 0 here. Let's see. So I'm graphing it, right? If I put in a y value as a function of x. 0 squared is 0. Let me pick y of 1. 1 squared is 1. Let me pick a y value of 2. That x value would be 4. Since it is y squared equals x, it is a sideways parabola. Literally, y, there's multiple y's for a single value of x. It's not undefined because if I pick this point right here, there will be a slope. Find the slope at this point. So I'm going to find the slope right here. And I'm going to find the slope right here. So if I want the slope, so if I want the derivative, the slope at 4, 2, I just have to plug in, let's see, 1 over 2 times my y. So 2 times my y, which is 2, is 1/4. And if I want the slope, one thing to note, slope is your derivative, right? If you take derivative at a point, you literally just found the slope of your tangent line at 4, -2. This is going to be 1 over 2 times -2, so that's just going to be -1/4. So, here's the deal. Ready? You took derivative on the right side. Easy peasy. Derivative of x is just 1. Take derivative on the left side. So this is, I think, where Tal's question was. Where the heck did the 2y come from? Imagine this was x squared. What would the derivative be? 2x, right? So more or less, this is not math terms that are coming out, but I'm trying to have you like understand the process, even if you don't understand why this works or why it's a thing. So you take the y, right? Take the derivative as a like just following the rules of x for derivatives, and then you have to tack on and multiply by this dy dx. It's just gonna take practice. That's also why we have 2 days to go over this. Okay. Elliot, you have a question? No. No question. Okay, cool. So we just gotta practice. So, ready? First step. Take d dx of every single term. So I'm gonna do d dx of my x squared. I'm gonna do d dx of my y squared, and then I'm gonna do d dx of 25. Well, d dx, what we've been doing so far, we literally take the derivative with respect to x. Derivative of x squared is just 2x. And secretly you've been doing implicit differentiation, right? Because before, when you would do d dx of both sides, so going back to like a simple example, maybe this will show you a little better. What's the derivative of x? 1. What's the derivative of, if it was just y, it would be 1 times dy dx, and so then the 1 goes away. I don't know if that makes sense what I'm trying to show you. Let me write it on the right side. Because like, technically you have been doing implicit differentiation this whole time, you just didn't know it because it wasn't written that way. Maybe this is the example I should start with. So you know the right side would just be written as 2x. I could just write it nicely. And the left side, so you tack on a dy dx, and then you treat this as if it's just an, like with the regular rules of differentiation, what's the derivative of, if it was just y, it would just be 1, right? If it was just x, derivative of x is just 1. So 1 times dy dx, we never had to like solve for it before. We never had to like have y, we've never dealt with a y with other than an exponent of 1. So it's when you have an exponent other than 1, so here are the y squareds, when you have these circles and these like curly things, that's when you have to do the implicit because y has an exponent other than 1. So you tack on a dy dx, and then you act like you're just taking the regular derivative of it. Maybe, I don't know, maybe that helps, maybe it doesn't. Okay, so if I want the derivative of y squared, derivative of y squared is just going to be 2y multiplied by dy dx. Derivative of a constant is 0. We have to get dy dx by itself. Try to get it by itself. You say fun or done? Okay. Okay. That's good. It's hard introducing because it's so different. But it kind of makes sense. No.
So then once you get that, you have to fill in the
yeah.
Right? So you fill in the x and the y.
Okay, so we have to get this by itself first. So I subtract 2x. Oh, is this the same thing as beginning?
Yeah.
Surprise! It's a circle. It's the same slope. Okay. Why is this not working? Need a new tip. Subtract 2x from both sides. Divide by 2y. You get negative x over y. Alright, subtract 2x from both sides, then divide by 2y. Do we get to this point? Can we follow? Okay. It's going to be, I know it's going to be hard for you to do it by yourself. So, now I want to know dy dx, aka the derivative at 3, negative 4. That's just going to be negative x, so negative of 3 over negative 4 is going to be?
Negative 3 over 4.
3/4, yeah, negative 3/4.
Before, so because it would be negative over negative.
Yeah, because negative over negative cancels out. So I want the derivative. Where? And so you have the line and then the point underneath. That's like, where do we want the derivative at? Where are we evaluating? Oh, at this point, 3, negative 4. It's just the way it's written. Yeah. Cool. Okay. So take a second. Do we have questions? Are we done writing? I know we have questions. Don't worry. I know we have lots of questions. Yes.
So could you make it y equals negative x and then just do it equal?
Y equals negative x. Because it's dy dx equals negative x over y. So this is literally saying like f prime of x is negative y over x. So the weird thing is, normally our derivatives are in terms of x only. Now it's in terms of y, because now we have more than one y value for x per x. You know what I'm talking about when I'm saying this? If you have a circle, you have like 2 y values for a single x value.
So like it's.
So you could say y times f prime of x. You can't get at y by itself.
Well, but if you move it, so it's like 2x plus 2y equals 0.
2x plus 2y. It's not. It's 2y times dy dx. This is being multiplied.
You would still get 3/4 because the slope.
What?
It's, okay. Just like, never, I think it's easy.
Try to. Okay. So this next one, we're gonna find dy dx of 2y equals x squared plus sine y. So this one we have more than one function that depends on y. So I'm gonna rewrite this. So I have 2y plus x squared. Come on, why? It's always your class. This is always the one that like stops recording and doing all this crap on. Okay, plus x squared. No wait, equals 2y equals x squared plus sine y. Do you have any idea what this looks like? No. Okay. Let's put in our calculator. Maybe you'll better understand when to use implicit if you like see it.
2x over 2 minus sine y.
2x over 2 minus cosine y.
What are QPs listed, Brian?
Quick pull on your calculator. Because I want to see how we're doing first before I know what to write. Because it seemed like, I mean, for the most part, we were doing well on chain rule, so.
Yeah, I love Daniel.
Yep.
I don't know about that.
Okay, so I'm going to graph this. Alright, so it needs to be in relation mode because this is not a function. Okay, so it's going to be 2y equals x squared plus sine y. Oops, hold on, relation. I have to do different. Oh my gosh. I don't want to do parametric though. Oh, I don't want this. No, I don't have to solve for it. No, I'm not gonna do this. No, I'm done. I could, but I have a lot of tabs open. I'm not trying to open my internet while I'm screencasting. So 2y equals x squared plus sine y. It's this nasty looking, curvy, multiple y's for single x looking thing. Cool. So let's go ahead and let's take the derivative. What? Tall, please, tall, you're okay. Okay. So, okay. So, let's. Yes, it has. Okay. So let's ddx all these, aka let's take derivative with respect to x 90%. What? What's wrong? Ah. Okay. So, yeah, you guys are. All of you. Except Tolly and Maya.
I'm being so good.
Try-
Thanks.
Try to think. Who haven't I like had to chit chat today?
I haven't done it
We
today.
have been really good.
Huh?
We've just sat
Well, you like turn. You literally turn your whole head away from me.
Right.
I haven't done that today.
I took the clock.
on my calculator.
I've been really good today.
True.
Looking at the wrong.
Okay, so when you're taking dx and you have something other than y is not alone. If you it has a coefficient or maybe an exponent or something, you have to treat it. Yeah, treat it as if it's like, oh, take the derivative as if it was an x. So derivative would be 2, and then tack on a dy dx. The next one, this is in terms of x, so it's all good. The derivative of x squared is 2x. And then next, derivative of sine is going to be cosine of y. And then since it's in terms of y, I have to tack on a dy dx.
So if it's in terms of x, you just get rid of all these.
Yeah, because then it would be dx over dx. You're putting a
Oh, so
d...
technically you are doing it, but it just crosses out.
Right. So that's what I was trying to show. That's what I was trying to show at the beginning, and like everyone was looking like I was crazy.
I got it.
Right? Because I'm literally putting the variable. Yeah, I'm shushing you right now. You're literally turning and whispering to her, Spencer.
Ask me a question.
God.
Oh my.
So, right. Maya's thing. We're literally doing dx in terms of x. Well, guess what? The variable I'm taking derivative of is x. Dx over dx is just 1. That's why it disappears when I'm just doing the derivative for x. Okay, issue. Now I have 2 dy dx's. So I need to get them on the same side, factor it out, and get dy dx by itself. Yes, Noah?
So in the beginning, the first one says 2 times dy over dx. Why is it not 2y times dy over dx?
If I said 2x, what's the derivative of 2x? 2. So derivative of 2y is going to be 2 times dy dx.
So how come that one's close to?
Because it was sine y. Derivative of sine is cosine. You leave the inside angle. If it was cosine, hey, I'm adding on to your question. You got to pay attention. You can't just turn and talk immediately after. If it was cosine of y squared, you'd have to do chain rule. It would be cosine of y times 2y times dy dx. So imagine me throwing in chain rule when we're doing implicit. Okay. Subtract cosine y dy dx on both sides equals 2x. I'm trying to get dy dx on both sides. So I'm moving this term to the other side. Do you see how I subtracted it? No? Yeah? Okay. Then, guess what? Dy dx is a common factor, so I can pull it out. Don't have enough room. I have to pull it over here. Now what are you doing?
You got it, it's kind of funny.
So I pull out dy dx, and I literally have 2 minus cosine y is equal to 2x. So if I divide both sides by that, I see the derivative dy dx is going to be 2x over 2 minus cosine of y. And that's it. So it says, so originally the problem said, show the slope is defined at every point on the graph. Okay, etc., etc. We just want to find the derivative. Yes, Noah.
Okay, to be honest with you, like the last chapters when you do work, I see where you're coming from and see how you do it, and like I know how you do it and why you're doing it, so that's why I understand it. Like this, I'm just copying down what you're writing and I don't know what's going on.
I get a sentence
Okay.
that could have been a lot shorter.
I didn't follow the beginning.
Yeah. Okay, first thing I did, wrote down the equation. Then I go through, take the derivative with respect to x of every term. Now, if the term is just an x, cool. I can ignore the dx dx because that's just 1. Literally dx dx is 1. Same thing. But since I'm taking derivative with respect to x of a variable that's not x, y, I have to take the derivative of that variable and then tack on a dy dx at the end. So, right, taking the derivative every step, tacking on the dy dx, taking actual derivative every step, then getting all the dy terms with dy dx on one side, factor it out, and get it by itself. So after you take all the derivatives, your goal is to get them all on one side and get dy dx by itself. Elliot?
What is the difference between how do you find the different derivatives? Like, what's the difference?
Like, are you talking about the
Like d dx and dy dx. What's the difference?
d dx with something in the parentheses means take the derivative of this thing with respect to x. But dy dx says, hey, the derivative of y with respect to x.
So
It's like a verb versus a noun, right? d dx is a verb. You actually have to do something. You have to take the derivative. Where dy dx is like a noun because it's literally the name. It's like, this is the derivative.
That's why you didn't an answer. It's like here you.
Yeah. Yeah. Oh, this is good. You get it.
I do. I don't know.
I do
She's the
not.
only person in the class.
Okay.
Because it's like a verb noun thing. That makes a lot of sense. What? Yeah.
Good. Because if
It's
you
like
have.
that's actually doing it, but then when you put your answer, like when we look for y or whatever,
This
at
is-
the end when you answer, you do like f of y prime equals, like you write the whole thing out. Do I sound like I'm talking in another language? No,
No.
What do you
I
do?
know what you're saying.
This is so
But what do you do?
What do you mean? What do I
What do
do?
you do? You find the derivatives.
What?
You do the verb.
Yes.
Which you find the derivative.
Yes. And then.
And then what? You just write the answer.
So yeah, I'm getting the idea after that is just like, hey, I have dy dx, get them all on the same side, isolate it by itself. So all the work after this is trying to get dy dx by itself. Literally, ready? This whole thing right here, this is all just to get dy dx by itself. That way I have the derivative alone. Because dy dx means derivative.
So what's the difference between this and what we were doing before?
Notice that our answer has y in it. Normally, dy dx is in terms of only x. This is in terms of y and x.
Aren't you only supposed to find one?
Okay.
How do you?
Wait.
So, if you look at 3.6, all the notes. All the derivatives only had x in it. Cosine of x, sine of x, blah, x is la la la, whatever. There were no y's in our answer. The only y you saw was in the dy. Notice all these have a y in the answer. Oh, it's minus, cosine of y is on bottom. Here, over y. We didn't have an answer with y in our derivative before. Now we do. Yes. Elliot, then talk.
Forgetting about the fact that there's a y. In practicality, you do it exactly the same as we did before.
Yes, that's exactly. You're just tacking on a dy dx to the derivative of y. That's what I've been saying over and over again. Just tack on a dy dx.
Is it ever gonna find
Okay,
you?
fine.
Ask me to
I
find
get
it.
it. You did? Yes.
What?
Is it ever gonna ask me to find it just as one of them? It's not dy dx.
So it doesn't make.
Then how would you solve?
So I can't ask you. It does. Okay. So it doesn't make sense to ask like, what is d dx? Because that makes no sense. Derivative of x, like with respect to what?
Point.
Huh? I'm trying to think of like a parallel to ask you that would be like, it's kind of like asking you. It's kind of like only saying a noun, and you're like, you're waiting for the verb. You're like, what do you mean? I could say tall, and you're like, yes, what? Tall. I want you to go, like, do what, right? I'm not finishing my sentence. If you just say d dx, it's not finishing your sentence unless you're actually taking a derivative of something. Okay, implicit differentiation process. How do you do it? Differentiate both sides with respect to x. This should have been at the beginning. Collect the terms of dy dx on one side. Factor it out and solve.
Oh my god.
It's like Jeremy and Maya last year.
I just, I don't know what to do besides kick half of you out. Like, I don't know. I don't know. Let's do this. Let's try to finish this one. First step, differentiate both sides of the equation with respect to x. I'm gonna write this out. X squared minus xy plus y squared equals 7. Now, magical fairy wand. Bzoof. Now I want to take derivative of everything.
D over dx over.
D over dx,
Wow.
everything.
This is what I mean. Why is it just d over dx?
This is the verb.
So, but I'm not just writing d dx. Look, I have parentheses around it. Right?
When does your y dx?
When I have a y. Like the next term. Oh, good. So, notice the second term is taking x times y. I'm taking a product of x times y. So I have to use the product rule. Oh my gosh. Maybe.
Oh, pretty good.
Just preparing you for what we're going to do. Cool. Plus,
But it's still just
I did
one.
do that.
okay. First one, chill. It's just 2x, right? Minus, ooh, I have to do product rule. Do you remember product rule?
But it's one.
Oh.
You-
U
One-
v1
one-
over
one-
v
one-
plus v1 u.
1 times dy dx.
See what?
U v1 plus v1.
It's one, it's one plus it's one.
So you said when you're taking a y, you dy dx.
Yeah, I'm not done yet. This is product rule. Product rule. Product rule, yeah? I circled product rule. Okay, so the first one's u. So I take x times the derivative of y. Okay, derivative of y is just going to be 1 times dy dx plus rv times u prime. So it's just times 1. All right, so I'm letting x be my u, right? And the derivative of x is just 1. I'm letting my v be my y, and the derivative of of y would be 1. And remember, we have to tack on the dy dx. So that's where, like, I'm using up here to show you how I plugged into my product rule that I just wrote. Okay. Then let me just finish the line. So add 2y, because derivative of y squared is just 2y. It's the same rules times dy dx. So we're taking derivative of something other than x, aka y's. That's all I'm going to ask you is y's. Tack on a dy dx equals 0. Okay,
So was it big bracket?
because this is showing you the product rule I did.
I get that still, but what? Never mind.
It's showing you the product rule.
Line, probably.
Okay, I'm going to rewrite this. So I have 2x minus x dy dx. And don't forget to distribute the negative. Minus y plus 2y dx over dy dx equals 0. It is. These two terms can go to the other side. So I have y minus 2x. Right, because I add y to both sides, subtract 2x from both sides. Then I'm left with, notice that these two terms now,
dy dx.
you can factor it out.
Negative.
Oh, and then you divide.
2y.
What is that? Who is she?
So
Oh,
these
y minus
two,
2x over negative x minus 2. Is it 1?
2y minus x. No, it's not.
You're like, no.
It's okay. It's okay. So, so I factored out dy. I'm left with this factor. Okay, 2y minus x. I have to divide both sides.
Y minus x. Oh, yeah.
Okay, so we found this derivative, and the last part is have to plug in at a point.
It's the point.
Actually-
they gave us the most.
Damn it, that's not the end. Okay, so we still have a minute. Okay, so I found the derivative equation. I want it at a point, -1, 2. So I want to know what is the derivative, aka the slope. But I'm at a certain point. So I'm saying, okay, I want to find the derivative, but where? Oh, at a certain point. So I'm plugging this in. 2 minus 2 times my x over 2 times my y minus my x. So the derivative turns out to be 4/5.
Yeah.
Okay, and then the last part is the normal and tangent line. So it's just y minus, let's see. Oh, we literally have the point. Y minus 2 equals 4/5 x plus 1, right? This comes from the fact that our x comma y was -1, 2. And then that's the normal, I'm sorry, that's the tangent, and the normal, same numbers. You flip it and change the sign of your slope.
So you just put it in the.
I just put in point slope form, the normal and the tangent, and then that's it. Literally, point slope, done. Wonderful.